Welcome to these lectures on algebraic geometry and commutative algebra. Last couple of lectures we were studying rings of fractions, especially the ideal structure in them and also the prime ideal structure in them. Today we will do modules of fractions, which is a similar construction, and I will be at times brief because the checking is similar to what we have done in the case of rings of fractions. So, modules of fractions. Also called localization of modules. So, we fix the notation. So, let as usual A be a ring, always commutative, and now we are studying modules over the ring A. So, and as usual A mod, this is the category of A modules. As I keep saying, category of A modules is by, it's a big data. So, its objects are the modules over the ring A, and the morphism between the two objects, that is morphism between the two A modules, are the A module homomorphism from between them. So, and let S be a multiplicatively closed set typical examples. We will apply this theory for S equal to either generated by one element, that is this set for a fixed A in A, or S is a complement of the prime ideal A minus P, where P is a prime ideal, or also S is non-zero divisors in the ring A in ZDA. This is a set of non-zero divisors in A. Or we can also take finitely many prime ideals and the union of their complements. So, more general than this, we can also take finitely many prime ideals and their complement of their union. Alright, so in this situation, and let V be an A module. Then we are going to define, so definition, we are defining S inverse of V. This is by definition on the product set S cross V, we have an equivalence relation. So, where this is a quotient set, where this is an equivalence relation on S cross V defined by, you take any element S comma X related to T comma Y. This is if and only if. This is a definition. Think of this as a fraction S over A, X over S, this as Y over T, and cross multiply and multiply by an element of S. So, there exists an element S prime in S such that S prime times Tx minus Sy is 0. And equivalence class of the element S comma X under this relation, equivalence relation, is denoted by the fraction X over S. This is an element in the quotient set. And therefore, this one is by definition the equivalence classes which we have written X over S, where X varies in V and S varies in S. This is exactly similar to that of rings what we have done. Now here I want you to, I will remind you to check several things which I will not do. First of all, one has to check that this is an equivalence relation. So that is, it is reflexive, symmetric and transitive. Then we have to check, so that is one, and then this is the quotient set. Now the next one is, I want to make this as a module over the ring. So we remember we have already constructed S inverse A. This is a ring which we obtained from A, and we have also have this iota map, iota of S, and I will write A here also today. This is a ring homomorphism. So, and we had a module here V, and we have defined a module S inverse V, and I want to check now this is has a natural structure of S inverse A module. So define first of all the addition on this S inverse A module, of course by using the addition in V. V was A module, so it is an abelian group. So that addition I will use it to define addition on this quotient set. So take any two elements X over S, Y over T, and I want to add them. This you define to be usual Tx plus Sy divided by St. So this is, we have done it for all X, Y in V and S, T in S. Now as usual we have to define, we have to check that, I will write here that check that this addition is well defined. That is, it does not depend on the representative class of the equivalence class. And with that S inverse A, S inverse V plus this is an abelian group. This is very easy to check. In fact, the inverse of, I will write here, minus of X by S is precisely minus X divided by S. This is for every X in V and S in S. Alright, so we have an abelian group now, and now similarly we can define a scalar multiplication. Define the scalar multiplication of the ring S inverse A on S inverse V. This is of course by using the scalar multiplication of A on V. Alright, so how to define? So we are defining a map from S inverse V S inverse A cross S inverse V to again in S inverse V, which should satisfy the properties for the module. That means it should be distributive over the addition, and it should satisfy the compatibility conditions on the additive structure on S inverse V. So, take any element of A that looks like S inverse A, that looks like A by S, and this looks like X by T, and I want to send it to, naturally you send it to AX by ST, where AX is the scalar multiplication of A on X, and this is the usual equivalence class again. So, this we have defined it for A in A, S in S, T in S, and X in V. And again we need to check that this is well defined. This is what we need to check. And now I would simply say check that with this addition and scalar multiplication, S inverse V is an S inverse A module. So, you get a natural structure of the ring S inverse the natural structure on the S inverse V as a S inverse A module. Now, the most important property that we have used in case of rings of fractions is the universal property, and even in this case that is very important. So, let us state it: universal property of S inverse on modules. So, our notation is as above. All right. So, I forgot here, so I brought you to this page because we have also natural map, the quotient map that I want to denote. The quotient map from V to S cross V, and then we have the quotient map, that is S inverse V, and this is a natural map. This I am going to denote by iota suffix x and the module V. Now, this is necessary because it will become more clearer what we are talking about. So, both the suffixes are important, but when the notation is fixed and there is no chance of confusion, we should drop them. So, what is this quotient map? So, there is a x here, x goes to 1 comma x, and then it goes to the equivalence class, that is x over 1. So, this is the iota map. So, this map will play an important role in the universal property. So, what is the universal property? So, what is given now? As usual, we have given A is a ring, S is a multiplicatively closed set, closed subset, and V and W two A modules. And we have given a module homomorphism from V to W, and F is a module homomorphism V to W, A module homomorphism. given this data, the universal property says there exists a unique S inverse A module homomorphism which I will denote by S inverse F. This is from S inverse V to S inverse W such that the following diagram is commutative. Is commutative. So, what is the diagram? So, V to W, this is given to us, and then from V to we have this iota map, this is to S inverse V. Remember, this is S inverse of, not S inverse, this is iota Vs. This is that map. Then similarly we have a map from W to S inverse W. This is iota Ws, and we are saying there exists a map here. This is S inverse F such that this diagram is commutative, means you start from here, go follow it by F and then come back by this iota Ws. On the other hand, you go by this way, the results are same. So, that means F then compose with iota Ws, there is no dot on iota. On the other hand, this is same as iota first and then S inverse F. So, S inverse F compose with iota Vs. Then we say that this diagram is commutative. And we want to define S inverse map in such a way that it is S inverse A linear. Both these are modules over S inverse A, the ring S inverse A. So, it makes sense to talk about A module homomorphism. Now, most of the things are merely checking once you write the definition of S inverse F. So, let me just for the proof. So, proof. So, define I want to define this. So, and I want this diagram to be commutative. So, let me analyze where do V should go. V goes to, so node, so the demand is what? I will write here demand, this is a force for us. So, any x go to f of x and then come here, that we know x goes to f of x and then go to S inverse W, that is f of x fraction 1. This is the one way, and this should be true for every x in V. The other side, x, we started with x here, go here. So, that means we are going to x over 1 and then we are going to, this is the iota map, this is iota map, this is also iota map. Now, it is clear when I say iota means this is iota W, this is iota V. So, this is x over 1 and then where should it go? It goes to S inverse F. What will it do? So, that should do this. So, whatever we call it here, that is S inverse F of x over 1, that should be equal to this. So, this is what the clue we got. Alright, so we will define, so this gives a clue. So, for for x in V and S in S, and we want this to be S inverse A linear also, S inverse A module. So, we want it linear over. So, that means if I multiply by 1 over S, it should go inside. Similarly here. So, therefore, that prompts us to define the following: for x in V, S in S, define S inverse of F evaluated at x by S by f of x divided by S. This makes sense. This is our definition. Now, what do you want? What should we check? First of all, there are a couple of things to be checked, which I will abbreviate here. Check that first of all, we have to check that S inverse F is well defined. That is, it does not depend on the representative class, a representative element of the class x over S. That is what we have to check. So, if you take some x prime over S prime and x over S equal to x prime over S prime, then this result should not change. That check it. The another thing to check is that S inverse F is additive. It respects the addition. That is where you will need to use the fact that this is a module homomorphism. That means F is an additive map. Then you have to check that S inverse F is S inverse A linear. This is what. So, if you write down the definitions correctly and then you check one by one, that is very clear. So, I will not check this. So, but this is very, very important. So, one should always check it. Alright. So, next now, so some note, some important notes I will make. So note that if I take V equal to W and F equal to the identity map on V, then S inverse of identity map on V, this will be identity map on S inverse of V. This is very clear because we know how we have defined. So, S inverse of identity map is what? S inverse of IDV defined on x by S is by definition, this is ID I have to apply to x. So, that is IDX, IDV on x divided by S, but this is x by S and this is then ID S inverse V, no need to put a bracket there, evaluated at x over S. This is true for all x in V and S in S. So, this equality precisely means this equality. So, identity, if you take identity module homomorphism, it goes to the identity module homomorphism. The second one is, if I take two modules V, three modules V, W, or maybe let me use the different notation now, V prime, V and V double prime, 3A modules, and the module homomorphism between them F prime and F. So, F belongs to, see, instead of writing this arrow also one will write F prime belongs to the home A V prime V, homomorphism as module homomorphism from V prime to V, and F is a module homomorphism from V to V double prime. Then composition, we know f prime composition f. This is again f compose f prime. This is a modulo homomorphism, A modulo homomorphism from V prime to V double prime. So that is how these morphisms are defined. They have this property that if I take two modulo homomorphism, then the composition is also modulo homomorphism. Now if I apply S inverse to this, and so what do I get? I get S inverse V to S inverse V prime to S inverse V. This is S inverse F prime. This is what we defined, and then S inverse of V double prime, that is S inverse of F. On the other hand, I could have directly defined S inverse of this module or this modulo homomorphism F compose F prime. So this will be S inverse of F compose F prime. Now one should check that if I take their composition, that is same thing as this. So S inverse of F compose F prime is same thing as S inverse F, and then compose with S inverse of F prime. And these are very two important properties. So I will put them in a box, and this one. And how do we check this? Let us check quickly. So I want to check these two these two sides are equal and both are maps on S inverse V. So if I take any element of S inverse V, so x prime in V prime and S in S, then let us evaluate this side on x by S, x prime by S. And what do I get? This evaluated an S inverse of F compose F prime evaluated an x by x prime by S. This is by definition. Apply this map to the numerator, that is F compose F prime applied to x, and denominator is same as. But this is composition. So this is F of F prime of, this is x prime divided by S. But by the same logic, this is same as S inverse of F applied on the element F prime x prime, denominator is S. Now it is, we have checked that this is linear map. So 1 by S will come out, and then so this is same as, this one is same as S inverse of F, and where is it evaluated? That is S inverse of F prime evaluated at x prime by S, and both they are same as this. This side is also this and this side is also this. So we have checked this equality. This is for every x prime in V prime and S in V. So that means we have checked this equality. So the checking is very simple. One has to write it what we want and patiently check it by definition. So both these properties are so important, they are also known as, they are also called functorial properties. Functorial properties of S inverse. I will not say more about it today, but when I go on and when I have a precise language of categories and functors, these concepts will become more and more clear. Alright. So this means what? This means that S in, I want to think S inverse as a functor from the category of A modules to the category of S inverse A modules. So I will just record it, and then we will go on to the next proposition. Alright. So this means that this means that S inverse is a covariant functor from the category A mod of A modules to the category of category, I will denote that category also, S inverse A mod of S inverse A modules. So, that is we have this object to object, that any module V that goes to. Now, I will not use the same arrow, but I will use this arrow. This is the S inverse V module, and if I have a module homomorphism V to W F, then we have the module homomorphism this we have denoted S inverse F, and it satisfies those two properties, that if F is identity, then this is identity. If you have composite, if you have some other module now U and G here, then it is S inverse U, this is S inverse G, and then we know S inverse F composed with S inverse G, this is same as S inverse of G compose F. The word covariant, that refers to the arrow, the direction is same. And if you remember, in case of the spectrum, that arrow reverses. So, then in that case one can call it contravariant, but I will note it when we use this language more precisely. All right. Now, to go on, I need to define something. So, if I have a sequence, so definition. So, suppose I have a sequence of modules and module homomorphisms. So, something like this. So, this is arrow V n to V n plus 1, this is F n, then F n plus 1, this is V n plus 2, and so on, and this is also so on here. So, this may be finite or infinite. So, this is a sequence of A modules and A module homomorphisms. So, the maps are not just maps, but they are A module homomorphism. We call it exact, is called exact. If at each stage, here for example, here the kernel equal to the image, if kernel of f n plus 1 equal to image of f n for all n in whatever, wherever the index is. Let me write here n in n. Then we call it exact. More generally we call it complex, is called a sequence, above sequence is called a complex. If all the composite maps are 0, so that is f n compose Fn plus 1, they are 0 for all n in n. Then you call it a complex. Now let us see the relation between exactness as complex. So this means what? This is equivalent to saying image of Fn is contained in the kernel of Fn plus 1. Because it take any element in the image, that means it is Fn of some x, where x is coming from Vn. Then when you plug it in here, then that Fn plus 1 of Fn x is 0, therefore it is in the kernel of Fn plus 1. So that is equivalent. So a complex is exact. So okay, so once you have a complex, this inclusion only, may not be equal also. And then the nth homology, in this case nth homology of the complex, that also the shortly that long exact sequence big one, that is also denoted by V dot and F dot, that is a collection, right. So it is this is simply a notation Vn, Vn plus 1 and so on, this is Fn, this is Fn plus 1. So that is the long sequence. Complex, the homology of the complex, this is by definition that is denoted by Hn V dot, and usually that F is omitted in the notation, but if one should keep it for some time at least. This comma F dot, this is by definition the kernel Fn plus 1 quotient module by image Fn. This is a submodule of Vn, both these are submodules of Vn, and this is a quotient of those submodules. This is called the homology, nth homology. This is at each stage n in n, and therefore the complex, it's immediate from the definition, the complex V dot F is exact if and only if all the homologies are 0. For all n. So this is very useful. We will go on more about this once we have little more language with us, but this half I will stop now, and we will continue in the later half by some more properties with the localization of modules. Thank you. We will meet after the break.